Hello, my name is Anthony Atkinson.
And my name is Marco Riani.
We would like to continue working our way through our book that we have written with three other authors about robust statistics and monitoring, and today we will resume our discussion of the customer loyalty data. A strange feature of the customer loyalty data, which we analysed in a different video, is that we worked very hard and we improved the distribution of the residuals. It was nice to see that we got close to normality at the end of the process, but really nothing very much changed in the conclusions of the analysis. All the variables were highly significant when we started, and after our extensive investigations, they were more consistent, but nothing changed at all in the conclusions drawn from our analysis. Now we are going to contaminate those data and see if we can show some changes, the source of which can be revealed by our monitoring methods.
We start loading the data, and now we show a y-x plot. So the data that have been contaminated are most clearly evident in the panel of loyalty against negative publicity. Note that this contamination is such that some contaminated units overlap with the set of units that we discussed in the previous videos about
and identified as being outlined.
Start with the traditional analysis fit, using all the observations. It is worthwhile to notice that now the p-value of the t-statistic for negative publicity is high, suggesting that this variable is non-significant. Another thing to notice is the change in the value of r-square. Now the adjusted r-square is 0.646. Before it was 0.741
for the least squares analysis. So the model, in fact, is still fitting extremely well, despite this contamination.
We proceed by analyzing the QQ plot of studentized residuals and the symmetry plot of residuals.
It is quite clear from the QQ plot in the left-hand panel that there are a large number of negative residuals. The small residuals, there seems to be one line, and then for the larger residuals, there seems to be another line. There is none of the kind of bowing out and coming back to the diagonal of the plot that we saw before.
Now we move to the interactive part, and now we monitor the residuals, the scaled residuals during the search, and this is the plot, monitoring plot of scaled residuals.
It's quite clear now that especially in the lower tail, where there are negative residuals, there are a large number of them, and it's interesting to try to find out something about them by brushing.
And note that the decrease of these units at the end of the search. And this decrease causes a change in the ordering of all the other residuals. Now we brush these units.
Here this is a brush that includes 25 units,
and we check the position of the brushed units in the y-x plot. So these are the units which have been brushed. And you see that they generally correspond to the set of units that have been contaminated. As usual, you can click on a particular line, you can have information about a particular trajectory and the step in which the unit enters the search. We now move to the added variable plots. So with the automatic we find the outliers and find 51 outliers, and we call our routine for added variable, and then we highlight the units that have been declared as outliers. And this gives our figure 1041.
It is quite clear that, particularly for the lowest trajectory, the outlet, which is x6, the introduction of these outlying observations has an enormous effect. The variable goes from being highly significant to being non-significant. The effect on the other trajectories is nothing like so strong.
Yes, they remain significant. Now we do our automatic procedure for finding the best value of lambda, which in this case turns out to be 0.5. Then we store the outliers that have been found during the different searches for different values of lambda and produce the Venn plot, that is the monitoring plot of the score statistic for the 5 values of lambda for the Box-Cox transformation. And notice the trajectory for lambda is equal to 1. That is always outside, then comes back inside, and then goes back at the end. The percentage of outliers is very high when lambda is equal to 1, smaller for lambda is equal to 0.5, and then grows when you tend to analyze in a scale that is far from the appropriate one.
To recall that for the uncontaminated data, we found the square root transformation, that is lambda is equal to 0.5.
And then we do find the same transformation here in the case of contaminated data. Now we switch from the parametric world to the non-parametric. We start with the traditional EVAS. This plot is surprising because here there is no sign that something is wrong.
There's no sign also, of course, from the plot of transformed loyalty against loyalty that any transformation is needed. That is virtually a straight line.
The only one thing that you find strange is the transformation of price.
Well, there are also, if you look at the residuals against fitted values, there are sort of things for positive residuals. There's quite a lot of structure running out there, so perhaps there's something there too. But indeed, you were saying?
I was saying that here it is difficult to think that the transformation doesn't have to be monotonic. It's difficult to think that the relationship is non-monotonic.
Yeah.
Well, you can clearly explain the community outreach, then the transformation is positive and then starts to be negative, but this thing here, of course, cannot be explained. Now we go to the automatic model selection. We run our EVAS MS routine, and then we find our best solution. Notice that the automatic model selection procedure takes some time run, and now we see the best solution. Best solution has just 2 options: robustness and the need of having an initial parametric transformation. With the best solution, the value of a square is around 0.8. The 2 tests, Darby-Watson test and Jarque-Bera test, have a p-value which is much greater than 0.05. Therefore, the solution is absolutely reasonable. We check what happens with our best solution, and now we move to figure 1045. We have identified the units that have been contaminated. Note that now the transformed loyalty is not a straight line.
And there are, if you look at the plot of residuals against fitted values, there are now nicely separated outliers from the main body of the data, and the structure that we saw before in the sort of the flare up to the left-hand top corner has now completely disappeared.
Now we use the transformed observation using EVAS in order to show the final y-x plot. And here notice that the negative publicity has been reversed in sign.
Yes.
And also notice that the units that have been declared as outliers are a great subset of the units that had been contaminated. Remember that we had done a contamination in terms of price and negative publicity, so these outlying units mainly show up in these cutters. Well, now it is time to come to the conclusions for this example.
It is clear to us, and we hope to you from having seen this example, that the use of robust methods, together with monitoring incorrect structure, is the way to move forward and to find out properties of the data that are not evident from either non-robust methods or from static robust methods. In the least squares analysis, the residual plots indicated some kind of departure. The nature of this departure was made clearer by the monitoring plot that we have seen of the least squares residuals. The robust features of RAVAS detected outliers, removed them, and led to an interpretable model.
Right. In fact, notice that with simple RAVAS, once again, you didn't see anything at all. Thank you for watching, and see you to the next video.